Welcome to the Substation Primary Design course by Engineer Sharif Hussain. In Part 2, we focus on the key formulas for grounding calculations essential for substation safety and integrity. In this part, we delve deeply into the critical formulas for grounding calculations, including step voltage, touch voltage, ground potential rise, maximum grid current, ground resistance, and mesh voltage, all ensuring personnel safety and system reliability in substations. We begin with the step voltage, S-step, calculated using equation 10-3, which incorporates the reduction factor Cs for derating surface layer resistivity and other parameters to assess the voltage potential between a person's feet a step apart during a fault. Similarly, the touch voltage, touch, is determined by equation 10-4, which is vital for evaluating safety risks when personnel touch energized equipment and grounded structures simultaneously, preventing harmful body currents. The reduction factor Cs, defined in equation 10-6, accounts for derating the nominal surface layer resistivity. It equals 1 for no protective layer and less than 1 for a protective surface layer with higher resistivity. Next, we examine the ground potential rise, GPR, as per equation 10-2, which is the product of the maximum grid current Ig and the substation ground resistance Rg, indicating the maximum voltage elevation of the grid relative to remote earth during a ground fault. The maximum grid current, Ig, is the RMS symmetrical grid current, specifically the portion of the symmetrical ground fault current that flows between the grounding grid and the surrounding ground via the soil. Equation 10-8 calculates Ig, incorporating the current division factor SF, the breaker short circuit rating IF, and the decrement factor DF, providing the effective fault current into the grid. The current division factor, SF, relates the total fault current magnitude to the portion flowing into the ground. It is normally computed per IEEE 80 standards, but for National Grid Saudi Arabia applications, the minimum value is 0.7 unless specified otherwise in the project technical specification. The decrement factor, DF, accounts for the decay of fault current over time, but is typically taken as 1 for the entire fault duration, simplifying calculations as per industry standards. Substation ground resistance, Rg, is a critical parameter calculated using equation 10.13, representing the resistance from the grounding grid to remote earth. This formula incorporates average ground resistivity ρ in ohm meters, area A occupied by the grid in m superscript 2, total buried length of conductors LT in meters including rods if present, and grid depth H in meters, even under buildings. For substations, the ground resistance must be equivalent to 1 ohm or less to effectively dissipate fault currents and maintain safe voltage levels. Finally, we address mesh voltage, M, represented by equation 10-9, which determines the maximum voltage difference within a single mesh of the grounding grid. This equation includes soil resistivity ρ, spacing factor Km for mesh voltage, and corrective factor K for grid geometry, where K equals 0.644 plus 0.148 in as per equation 10.10, along with Ig and effective length Lm. The effective buried length, Lm, is crucial for mesh voltage calculations and varies. For grids with no rods or few scattered rods, Lm equals Lc plus Lr. Specific formulas apply for rods at corners, perimeter, and throughout the grid. Lm is calculated as the sum of grid conductors Lc and ground rods Lr, or adjusted using grid dimensions Lx, Li, and rod length Lr for configurations with rods strategically placed at corners, along the perimeter, or scattered. Understanding these formulas from IEEE 80 is essential for designing safe and efficient substation grounding systems that protect lives and equipment. Accurate grounding calculations specifically protect personnel from hazardous step voltages between feet and touch voltages to equipment during faults. They also ensure reliable operation of transformers and other electrical equipment by safely dissipating fault currents into the earth. These principles are fundamental for electrical engineering students and professionals involved in substation design, installation, and maintenance. Mastering these grounding calculations is key to developing safer, more robust electrical infrastructure compliant with standards like IEEE 80. We begin by examining equation 10.11, which calculates the step voltage, a critical parameter in grounding system design. Here, LS represents the effective buried conductor length in meters, a value derived from the grid's configuration, specifically 0.75 LC plus 0.85 LR for grids with or without ground rods. He is the corrective factor accounting for grid geometry, calculated as 0.644 plus 0.148 multiplied by N, the number of parallel conductors. Equation 10.12 further defines key. This equation helps refine the geometry factor, ensuring accurate calculations for various grid designs. Next, we delve into equation 10.14, which determines the thermal short-time current capacity of a conductor. Here, F represents the symmetrical ground fault current in kiloamperes, a critical value for system safety. A is the conductor cross-section in square millimeters, while Tm is the fusing temperature and Ta is the ambient temperature. Alpha T is the thermal coefficient of resistivity, and Rho T is the resistivity of the ground conductor at a reference temperature. Tc signifies the maximum possible clearing time, typically taken as 1 second, and TCAP is the thermal capacity factor from Table 10.1. Table 10.1 provides material constants for stranded, annealed, soft copper wire, including conductivity, alpha factor, Co, fusing temperature, and resistivity. These values are crucial for accurately calculating the thermal capacity of conductors under fault conditions. Moving on, Table 10.2 outlines recommended ground copper conductor sizes for various applications. For equipment ground conductors, sizes like 95, 120, 240, and 2 by 240 square millimeters are recommended. For the main ground grid in an embedded system, sizes vary based on fault current, such as 120 square millimeters for 25 kiloamperes and 31.5 kiloamperes, up to 240 square millimeters for 63 kiloamperes. A keynote states that the final conductor choice after calculation should be the nearest higher size shown in this table. Backfill materials are crucial when native soil resistivity is high, as they help achieve a smooth design calculation and ensure a safe grounding system. These engineered materials, with low resistivity, replace existing soil layers to optimize grounding performance. Now, let's walk through the ground design calculation procedure flowchart, Figure 10.2. The process begins with Step 1, collecting field data such as soil resistivity and maximum grid potential. Step 2 involves determining the conductor size based on fault current, clearing time, and conductor diameter. Step 3 establishes the touch and step criteria, defining tolerable potentials like a touch and S-step for safety. Step 4 involves the initial design, setting parameters such as grid dimensions, conductor lengths, and burial depth. Step 5 calculates the grid resistance using effective conductor lengths. Step 6 determines the grid current based on the fault current and clearing time. Step 7 checks if the product of grid current and resistance is less than the tolerable touch potential. If not, Step 8 calculates mesh and step voltages using various geometry factors. Steps 9 and 10 involve checking if M is less than at touch and ES is less than S-step, respectively. If any criteria are not met, Step 11 requires modifying the design parameters like D, N, LC, and LT, leading to an iterative process. Finally, if all safety criteria are satisfied, the process concludes with Step 12, the detailed design. End of Part 2 and wait for Part 3. Thanks for watching the video. Please share the video and subscribe to my channel.